Hi everybody, I'm Bryan Perozzi and I'm here to talk to you today about graph neural networks and graph embeddings. This is the first in a section about graph neural networks at our NeurIPS Expo workshop, and I'll be followed by my colleagues Amol Kapoor, John Palowich, and Alessandro Aposto. In this section, I'm going to talk about an overview of the area, and the following sections will be more of deep dives on recent work that we've done. Now, so first, I'm going to talk about graph embeddings, then I'm going to talk about graph convolutions, and then I'm going to talk about the challenges of graph neural networks on real data at an industrial scale. So a graph embedding is, it's kind of the primitive component of using a graph neural network. And the idea here is that you have sort of a graph, which is this discrete space where you have nodes connected by edges. But in order to reason about that with a neural network, you need to convert it to a continuous space. And the process of taking this discrete thing and mapping it into this continuous space is called embedding. Now, embeddings are much lower dimensional than the objects that they represent normally. So a graph might have billions of nodes, but the dimensionality of an embedding might only be, you might only use hundreds of dimensions for it. So it's a dimensionality reduction technique to transform a discrete object into a continuous one and hopefully represent as much of the same information as possible. Now, so you can think about this then as that a graph embedding is just a representation of a graph in a way that a neural network can understand. And it's supposed to preserve the properties of the graph. Initial work on graph embeddings focused on things like using reconstruction over random walks with an unsupervised loss to learn embeddings. And this paradigm for graph representation learning, kind of introduced by DeepWalk, was to choose a graph that you want to encode. Somehow convert that graph into samples, maybe pairs of entities that are close to each other, and then model that, so encode that information somehow. And the output, the latent representations of your model, are actually the embeddings that you use. And that's kind of the little flowchart on the right. This paradigm has been fairly prolific, so there's been a lot of riffs on it. But the core idea is that, this unsupervised graph embedding will try to just encode the graphs as they are. So you'll try to reconstruct the links. You'll try to preserve possibly attributed information about the nodes, but all you're doing is encoding. If you want to see what a picture of a graph embedding looks like, there's one kind of applied to the Cora citation network right there. And the colors correspond to labels. So you can see that if there are labels that correlate with community structure in your graph, your graph embedding will reflect that. And then you also see that there's sort of these weird communities that are formed in the space, and so you also can kind of preserve properties of that in the graph embedding as well. So since this unsupervised graph embedding came into being, there's been a lot of extensions of it. And in particular, my group has worked on things like extending these representations to work on undirected graphs. Initially, they were just for extending it to work on directed graphs. They were initially was just for undirected graphs, and so so we had this paper doing that. That's kind of the first idea here. Another thing we've looked at is using the hierarchical structure of graphs, right? So many graphs have patterns at different scales. So if you zoom out, you might see just like see a shape. You might see like a big ring, or you might see clumps of clusters. But if you zoom in, you see very different behavior. And using this hierarchical structure, either for pooling or initialization of embeddings, you can sometimes learn better embeddings than you could otherwise. And that's kind of what the second paper I'm highlighting here was about. We tried this hierarchical decomposition for learning better embeddings. And another thing we've looked at is applying attention to embedding models. So in another paper at NeurIPS a year or two ago, we had this graph attention. We applied a graph attention over the distances of nodes in the random walk and allowed the model to choose which distance it should learn to attend to in order to reconstruct the graph best. So perhaps it should only look at immediate connections, or perhaps it should look at long-range connections. It turns out in different graphs, different distances are best for reconstruction. So we've worked a lot in this area, but I don't really want to dive into this older work that we have. Now, I want to just kind of, I guess, say the moral of graphs as an embeddings is that once you have a graph embedding, you can sprinkle them into all different kinds of other models. And so the reason the graph embeddings are really powerful is because they allow us to encode graphs in a way that we can combine with other features like a image embedding or a video embedding or an audio embedding. And you can do this for graphs that have complex heterogeneous structure. So one of the real powers of graph embeddings, no matter how you learn them, if you learn them in an unsupervised way or a semi-supervised way, is that you're able to encode them and then kind of mix the relational representations or graph embeddings, whatever you want to call them, with another model in order to add a graph component to it. So that's kind of like the idea of graphs as a modality, which is something that we definitely advocate for. Now, I just talked about unsupervised graph embeddings, and of course, there's a desire to be able to learn them in a supervised way, right? If you have labeled information, you can improve the quality of your representations by applying it to your model. So I'm going to talk about graph convolutional networks, which are an extension of kind of this basic embedding idea in order to learn a deep model through a graph that can take advantage of node features and can use labels to do it in a semi-supervised way. Now, there are challenges when you do this. So the idea of, unlike convolutions in images, if you have an image convolution, it's a fixed size, so it's a grid. It's very easy to work with. But in graphs, you can have kind of an arbitrary number of edges connecting to each node. And so graph convolutions kind of at their core have to deal with the fact that they need to be able to handle an arbitrarily large number of nearby neighbors to use as part of the convolution. So this whole idea is all about taking the idea of convolutional neural networks from vision and trying to apply it to arbitrarily structured data. So now you probably at this point heard about adjacency matrices, but in case you're watching these out of order, I just want to talk about how we represent this graph internally. We use an adjacency matrix. Every node has an entry, a row, and a column that corresponds to it. And there's a non-zero entry in that row and column when there's an edge in the graph. So you can have different kinds of relationships. You can have different kinds of nodes, like the different shapes here represent different kinds of nodes. And you can use this to encode all of the graph structure into this matrix form. So what does a graph convolution look like then? Back to a node link diagram. So a graph convolution at its core, it takes a part of a graph centered around, let's say one node. It looks at the immediate neighbors, and you can think of these as kind of like in an image, CNN. This would be like the pixels around the immediate pixel, right? So you're going to take this, we call it the one-hop neighborhood sometimes. So the immediate neighbors of the seed node. And then maybe you go out further, you look at the two-hop neighborhood, their neighbors. So you get like a small subpatch of information around this node. Now the nodes here, they can have feature vectors. For the purposes of understanding, these feature vectors can just be an embedding of something about the nodes. If the nodes, for example, were websites, the feature vectors might be an encoding of an embedding of the text of that website. And therefore, these features are, every node has their own, and the links, in this example, maybe think of the links as the references between the websites. So a graph convolution then, you have a seed node, you have its features. You're going to take the features of the node and its neighbor, and you're going to project it into a new latent space. You're going to learn a new vector for the seed node. And this is essentially a graph embedding. You're going to do this for every node in the graph until you projected the whole graph into a new space. So now every node has its own latent vector that you've learned. And you can repeat this process multiple times to learn new latent vectors by combining the ones of your neighbors around you, and then using a loss at the top, like some labels or something, to actually train the network. And so this is like the core idea of the Graph Convolutional Network, that you use these features. You have features that you want to use for prediction. You can label, you can learn to label the nodes of the graph from the features when you have missing ones. And you can learn this embedding process like kind of jointly with your classification task. So you kind of learn this, you learn a graph embedding, like a semi-supervised graph embedding, and you use that graph embedding for classification. You can also do pooling. So it's not just node classification that's done this way. If you want to do link prediction, you can get the embeddings of two nodes, and then you can train the embeddings to be close to one another, just like an unsupervised embedding might. And so that's how you can use this kind of convolution idea for link prediction. Or you can do things like graph classification, where you keep pooling until you just have one vector that describes the entire graph. So you can kind of keep aggregating and aggregating until you get to a vector that describes the entire graph. And then you can do it for, you can use graph classification on that, or learn a graph embedding. So this graph convolution aggregation is very flexible and is used in many papers that you'll see at NeurIPS this year, undoubtedly. The Graph Convolutional Network, so one take on this, the GCN model by Kiff and Welling, it works in a manner similar to how I described, and this is just a little bit more formal. It's a sequence of multiplications between A, this normalized adjacency matrix, and then X at the first step. It multiplies A by X. It's just like multiplying the graph by the features, multiplying that by some learned weights W, passing that through a nonlinearity, and then that's where you get your new hidden state, H1. You kind of repeat that process. H1 gets multiplied by A, gets multiplied by a new set of parameters, W1, it's passed through a nonlinearity. And eventually you get to an embedding that you can use for some task like node labeling. So that idea is, the idea that I just presented is, if it's a flexible model, but it can be even more flexible. And in fact, I'll just go back for a second. So here, the matrix multiplication model inside the GCN is it's designed, because the graph is normalized in a very particular way. It's designed to basically be averaging. So you're averaging the features or the embeddings from your neighbor at each step. And in this follow-up work on message passing neural networks, they kind of generalize the idea of a GCN to be a little more flexible and to use sort of arbitrary aggregation functions and arbitrary message sending functions. So I want to take a minute or two to talk about this. And this is from the paper, Neural Message Passing for Quantum Chemistry. So in this MPNN model, it's just like the GCN we just talked about. Each node has a state. This is embedding. The initial states they come from somewhere. They can be either raw features, or they can be an encoded features, like the text on a website that's been compressed into a vector, like in our kind of previous example. And then when it's time to do to send messages from one node to another, instead of saying, hey, I have this fixed function, you say it can be general. So a message here can use the features of a node and the features of its neighbors. And you'll have a message generation function that can kind of take those two and kind of generate the message that should be sent from node B to node W here. So now you see it's more flexible. Instead of sort of saying only the my neighbor's features generate the message, it's saying, okay, learn how a message should be generated given these my features and my neighbor's features. Similarly, the states are updated by message passing, right? So that you have an aggregation. So you have, in one step, you have all the messages from your neighbors passed to you, and then you do an aggregation. It could be the average, it could be max, it could be sum, it could be attention over the neighbors. And you learn this actually as the output of some neural network too, right? So you learn to take the state of the node itself and the aggregated messages and compute the new hidden state, H1. So by linking these states together, you can repeat it. You can continue to update the next hidden state with the previous hidden state, and you can repeat this until you are done. So right? You'll get to a point where the model you've done it enough. In practice, this is normally kind of a hyperparameter, how many iterations of message passing to use. But then you can read out the final state and use that for some classification, from decisions such as classification for nodes or pooling for learning representations for graphs. So, I mean, we've barely scratched the surface. There's a lot more here. And the interest in this area is phenomenal. There's so many papers that have been published in the last year alone. So at one point in time, we actually sat down and we tried to group them together. And it's definitely a complicated task. You can see the taxonomy we developed here on the right of the screen. But one thing that we noticed is that these models share a lot of common elements. And so many models can be described by this encoder-decoder paradigm that we talk about here, the Graph EDM model. So if you're new to this area and you'd like to see a lot more, especially kind of a unifying treatment of many methods, you might want to check out this survey that we posted on Archive. It's a preprint, but hopefully you'll find it helpful. Okay, so I want to use the rest of my time to talk about challenges of graph neural networks. And like I said, this is something that we're going to talk about in the following sections too. So I'm not going to be able to address all the challenges right now. And the first challenge is kind of representation complexity. So remember the GCN, you're going to start a process. You start with a seed node, you aggregate it from its neighbors, you aggregate their neighbors, and you have the sequence of aggregations in order to create a multi-step embedding. And so it's this multiple aggregation process that's really one of the weaknesses. And the weakness here is that, the aggregation that you use matters a lot. I guess that's probably the best way of saying it. In the initial paper, actually, Kip and Welling show that adding extra layers after the second one doesn't improve the classification performance. So as the model gets deeper, it doesn't get better. In fact, it quickly levels off after 2 layers, which is not what you want if you're trying to build a deep model. So the question is, how can we address that? And or maybe the first question is, why does that happen? Well, one is because of this layer sequence of sequential aggregation that happens. So your local neighbor's features are much more important than the ones around it. The other reason is kind of over-averaging, right? So if you're doing things like averaging and you keep averaging over a bigger and bigger set, you kind of revert to just like whatever the mean of the data set is. So you lose any locality of your information. So the representations kind of become, this is kind of why they call it over-smoothing, the representations kind of become more similar. So we have examples of when that happens, such as, on a prediction task, you might only be capable of learning, that if you learn an aggregation that nodes that have the same color in this example are similar, you might not be able to distinguish that when, you have nodes that actually have opposite labels as their neighbors. So you if you learn like a simple average of all the blue nodes, but you're really trying to predict, should be predicting white, or all the white nodes and you should be predicting blue, you might not be able to do a good job when you have edges that don't correlate with the nodes you care about. So we spent a little bit of time tackling this. Our first take on it was this mixture of experts model where we fed several different GCNs, increasingly dense graphs that had more and more paths between the nodes. So in particular, we'd raise the graph to a power, which isn't well reflected by this diagram. But the idea here was that by using different graphs that capture different types of community structure, the mixture of experts was able to come up with a classification verdict that looked at this multi-scale behavior of the graph. And so it would kind of have one guess based on how similar you were to your immediate neighbors and one guess how similar you were to your community around you. And this, creates rich representations in principle, but the models are large and a little slow. So we had a follow-up work at ICML recently, and we took the same idea where we had this different scales of representation and put it into the filter itself. So it's more efficient and not nearly as memory as intensive. And so we can show that as the graphs have less and less correlation with the labels, we call that a low homophily, we're able to improve performance substantially over baseline methods. And so that's a paper MixHop. And in the following section, I'm going to talk about additional challenges of graph learning. So we're going to talk about how can we make GCNs fast, what biases might a graph neural network contain, and how can we model complex interactions, like when a node is a member of other communities. If you're interested in the papers we talked about, they're here, and I'm looking forward to chatting with you guys. Thanks.